Hello. Today we'll look at a very useful second order partial differential operator that we can associate with an Itô diffusion. So first, a definition. So let x equal xt, t greater than or equal to 0, be an Itô diffusion. All right. We define the infinitesimal generator A of xt as A of f at x is equal to the limit t goes to 0 from above, expectation of f xt minus f x over t, whenever this limit exists. Note that the superscript of the expectation indicates that the Itô diffusion starts at little x, at time 0. It's the same little x here. So there's the definition, and we denote by dA the set of all functions f from Rn to R such that AF at x exists for all x in Rn. Okay. So there's the definition. We now recall the form of a time homogeneous Itô diffusion. So in class we know that satisfied dxt equals bxt dt plus sigma xt dbt, and we also have that x at time 0 is little x. So this is the form of a time homogeneous Itô diffusion, where b is a function from Rn to Rn, sigma is a function from Rn to Rn by m, both satisfying the usual Lipschitz condition, and b is a Brownian motion in Rm. In Rn. So we would like to relate this differential operator to the coefficients in the diffusion. In order to do that, we'll need the following lemma. All right. Lemma. Let yt equal ytx be an Itô process satisfying or of the following form. Ytx is equal to x plus the integral 0 to t u of s omega ds plus integral 0 to t vs omega dvs omega. And here b is a Brownian motion in Rm again. In Rm. Y is an Itô process in Rn. So y is in Rm. Okay, so now we let f be a C2 function from Rn to R with compact support. All right. We also let tau be an FMT stopping time where FMT is the natural filtration of the Brownian motion. And we also suppose that the expectation of tau is finite. That is, tau is almost surely finite. So we have this, and lastly, we assume that u t omega and v t omega are bounded on the following set. Bounded on the set S of t omega in R plus cross omega such that yt omega is in the support of F. That is the set of t omega such that f of y t omega is not 0. So with all of those assumptions, we have the expectation of f of y tau is equal to f of x plus the expectation integral 0 to tau sum over I ui s omega del f del xi ys plus 1 over 2 sum ij v transpose ij s omega del squared f del xi del xj evaluated ys ds. So we have this. Okay, so now for the proof. So for notational convenience, we're going to suppress the time indices on y and b so that we can use the subscript to specify the components of y and b. And also, before we apply Ito's formula, we note that due to the form of y, we can write that dyi, again, this I is not a time index, it's a component of y. We have dyi is equal to ui dt plus v db I, which we can write as ui dt plus sum over k vik dbk. Okay, so we will use this later. First, we need to apply Ito's formula. So let's do that now. We'll apply it to f of y. Okay. All right, so I'll continue up here. So we have that dfy by Ito's formula is the sum over I ui, sorry, not ui, nope, that's not right, del f del xi y, what do we have here? We have dyi, that's right, dyi plus 1/2 the sum over ij del squared f del xi del xj y d mutual variation of yi and yj. Okay, so now we're going to use this. We're gonna substitute this in here, and we also note that the mutual variation of two processes only cares about the martingale component, which is going to be the vdbi and the vdbj. So that's what will show up there. So we can write this as sum over I ui del f del xi dt. And here we suppress the input for the partials, just for convenience. So over I, now we have del f del xi v db So we write it in the shorter form. And then now we have plus 1/2 sum over ij. We have del squared f del xi del xj v dbi and v dbj. Okay, so now we're going to examine this term a little bit more closely. So we see that v dbi times v dbj. Okay, so we write it in the sum notation. We have this is equal to the sum over k vik dbk times the sum over n vjn dbn. Okay, which we can now write as the sum over kn vik bjn d mutual variation of bk and bn. All right, but we know that the mutual variation will be 0 if k is not equal to n, and dt if k equals n. So that is, we're going to have, this is 0 for k not equal to n, and dt if k equals n, since b is a Brownian motion in Rm. Okay, and so we can thus write this only with the terms where k is equal to n, and the mutual variation will be dt. Or sorry, the mutual variation will be t, but then we're doing d of it. So we have sum over k, vik, vjk, dt. And if we notice what's going on here, we're doing inner products of the rows of v. Inner products, yes, inner product of the rows, that's right. And so we can write this as VV transpose, because the columns of V transpose are the rows of V, okay? And when you do the matrix multiplication, you end up getting inner products of the rows, okay? So we can write this as simply the ijth entry, of VV transpose dt. So we have this is equal to this, and so we can now we can use this in this part of the expression, and we could also we're also going to switch over to the integral form of Ito's formula instead of the differential form. So we can now write, and we'll bring back the time index for y for these first two arguments. We have y f of yt is equal to f of y0 plus, and here we're going to have an integral 0 to t sum over I ui del f del xi plus 1/2 sum over I and j of VV transpose ij del squared f del xi del xj ds plus these remaining integrals. These will be stochastic integrals. This term here. So we're going to have sum over I and k, integral indicator function 0 to t of vik del f del xi db. What will we have here? Yes, no, we're evaluating this at That's y, but then yeah, we're gonna have dbk. dbk, all right. And so we're now going to take the expectation of both sides of this. And what do we get? Well, here's what we get. We're gonna get expectation f of y, and with tau instead of t, which is okay since it's almost surely finite. So we have expectation f of y tau is equal to, and now the expectation is given given the Itô diffusion y is 0 at time 0. So that means that the expectation of f of y at time 0 is just going to be f of the starting point. Okay, and we get plus the expectation of the integral from 0 to tau, the sum over I, ui del f del xi y plus 1/2 sum over I and j v transpose ij del squared f del xi del xj y ds, plus, due to the linearity of expectation, we have sum over ik, the expectation of the stochastic integral 0 to tau vik del f del xi y dbk. Okay, so these first two terms, fx and this expectation, are in the formula that we want to get. So we just need to show that this last term is 0. So yeah, to show that this last term is 0, we're going to just fix I and k basically and look at this function. So we know that this partial is bounded because f is C2 and has compact support. So this partial is bounded. Now we know that Vik is bounded on the set of T omega in R plus cross omega, such that Y T omega is in the support of F. So it's bounded whenever this partial could potentially be non-zero. But outside of that set, where V could potentially be unbounded, since the argument of this partial is Y, we know that F will be 0 there, which means that the partial will be 0 as well. So there's no problem with boundedness. And just for notational simplicity, we'll just suppose we have a bounded function g, which is this function for fixed I and k. So we suppose we have a bounded function g. And we're gonna conclude a few things and show that this term actually ends up being 0 for all ik. So let me just erase this. All right. So let's suppose we have a function g that's bounded by m. Now, for all k non-negative integers, we can write the following. We can write that the expectation of the stochastic integral, indicator 0 to tau min k, g ys dbs. This is nothing but expectation of the integral, stochastic integral, indicator function 0 to k, indicator function s less than tau, gys dbs, which is actually 0 because gys and the indicator s less than tau are both f ms measurable, where this is the natural filtration of the Brownian motion. So we have that this is 0. So that being measurable means this is a 0 mean martingale, so this is 0. So we now want to show that this integral indicator 0 to tau min k g ys dbs converges in L2 to the to the integral indicator function 0 to tau, gys dbs. So we have the expectation of the integral indicator function 0 to tau gys dbs minus the integral stochastic integral indicator 0 to tau min k gys dbs. So this difference squared, the expectation of that squared, okay, is, well, first we'll simplify the integral because of the indicator functions. So we have, this is the stochastic integral of tau min k to tau of gys dbs squared. All right. So we have this. It's measurable with respect to the Brownian motion, and so by Ito's isometry, by the Ito isometry, and the fact that the Doléan measure of Brownian motion is the product measure, is the product measure dt tensor dp, we can write this as the expectation of the integral tau min k to tau g squared ys ds, where this is no longer a stochastic integral, this is a Lebesgue-Stieltjes integral. And we know that g is bounded by m, which means that g squared is bounded by m squared. So we can bound this quantity by m squared and then times the expectation of the measure of the interval, which is going to be expectation tau minus tau min k. And since tau is assumed almost surely finite, we have that this goes to 0 as k goes to infinity. And what we've just shown is that the integral, stochastic integral with the indicator 0 to tau min k goes to the process with the indicator 0 to tau in L2, and hence in probability. So now we can say that 0 is equal to the expectation of stochastic integral 0 tau min k gys dbs. This is true for all k and n, so it's also true in the limit k goes to infinity, but by what we just proved, this is nothing but expectation of the integral, the indicator function 0 tau, oh, pardon my handwriting, 0 tau, of gys dbs. And so all of these terms are of this form. This function's bounded by some m for any ik, and thus it vanishes, and we are left with the formula that we were after. And this completes the proof of the lemma. So we now proved that lemma, but we want to go back to the form of a time homogeneous Itô diffusion and find a slightly more explicitly. So we have a theorem for that. Okay, so theorem. So let x equals xt, t greater than or equal to 0. Let x equals xt, t greater than or equal to 0 be an Itô diffusion satisfying dxt equals b xt dt plus sigma xt dbt. And x at time 0 is little x, where again, b is Rn to Rn, sigma is Rn to Rn by m, satisfying the usual Lipschitz condition, and this is a Brownian motion in Rm, and x is in Rn, Brownian motion is in Rm. Okay, so we have this Itô diffusion, and now we let f be a C2 function from Rn to R with compact support. Then we have that f is in a set of functions where the limit exists, and the limit is a f x is equal to the sum over I bi x del f del xi plus 1/2 sum over ij sigma transpose ij x del squared f del xi del xj. And this is what we have. And the proof, very simple proof, and it actually follows from the definition of A at the start of this lecture. From that definition and from the previous lemma using tau equals t. So we're just using we're using tau equals t here. All right. So we now go on to do a few examples. So using this formula, we'll do a few examples. Two examples, if there's time. Two examples, yep. So here we have the first example. So let's consider the diffusion satisfying dx t equals dbt, where this is an Itô diffusion in Rn, and we see that the n-dimensional Brownian motion satisfies this diffusion. So the Brownian motion in Rn. And so in this case, what we have is that b equals 0, and sigma is equal to the n by n identity matrix, which means that sigma transpose is also equal to the n by n identity matrix. And so using this formula, we see that for a suitable f, for f C2 on Rn with compact support, we have that the infinitesimal generator A is given by, so b is 0, so we don't get this, we get these terms, so 1/2 sum over ij, the identity matrix, ij, del squared f, del xi, del xj. And so we see that the entries of the identity matrix are along the diagonal, which means that the ijth component will be 0 if I is not equal to j, and will be 1 if I equals j, which means that the generator picks up only the terms where I equals j. And we get that the generator of Brownian motion is 1/2 sum over I del squared f del xi squared, which is simply 1/2 the Laplacian operator. So that's the first example. We now do one more example. I'm going over time. Yeah, you'll have to forgive me. I'm running in the red here. But let's just get one more example in here. We're going to suppose that x equals x1, x2 transpose, x1, x2 transpose, satisfying the diffusion dx1 equals dt, dx2 equals dbt, and where x1 at time 0 is t0, and x2 at 0 is x0. And so in some sense, this is the graph of the one-dimensional Brownian motion. Oh yeah, sorry, this B is a Brownian motion in R. So the one-dimensional Brownian motion. So this is essentially the graph of Brownian motion. And we can also rewrite this as dx, the vector x, dx is equal to b dt plus, b dt plus sigma dbt, where b is the vectors 1, 0, and sigma is 0, 1, which means that sigma transpose is going to be 0, 0, 0, 1, which means the generator is only going to pick up the del squared f del x squared components. We'll call this component the t component, and this is the x component of our x here. And so what do we get? With the formula, we have that AF is going to equal del F del T plus 1/2 del squared F del x squared. And this particular operator is known as the heat operator. This concludes today's discussion about the infinitesimal generator for an Itô diffusion. I hope you enjoyed.